Okay, this is about buffers. So the definition for buffers, which I taught wrong for many years because I forgot one word the IB likes to see, is that a buffer resists a change in pH when a small amount of an acid or base is added. That gets you your 1 point. Let's start with an acidic buffer first. So it's made with a weak acid, such as methanoic acid, and the salt of a weak acid, sodium methanoate, for example. So here's a dissociation of methanoic acid, splits up to form the methanoate ion, and that proton, that H plus, has popped off there. And these aren't the exact numbers, but almost all of it is undissociated, since it's a weak acid. That H plus there has come off of the methanoic acid and is available to do chemistry. It's the hydronium ion, if you will. But that H is still locked into the methanoic acid. It's not available to do chemistry. It's locked in. It's not acidic. If I add a base, it reacts with the only positive thing in the equation, forms water, and is removed. The equilibrium shifts to the products to replace the lost product. And I can add some more base, and it will form water. That's gone. And we can keep doing this all day, because there's loads and loads of undissociated methanoic acid, and it can keep shifting to the right to replace the lost proton, or H+. But if I add H+, it's going to shift back to the reactants, and there's going to be a problem. There's very little methanoate ion available to shift back, and so once that little bit's been used up, my buffer's not going to absorb any more H+. It can't really buffer against the hydrogen ion, just methanoic acid on its own. The HCO2 minus runs out, so add some more. If it runs out, add some more. Well, where can I find it? In the salt of the weak acid. That will 100% dissociate and just fill my buffer with this methanoate ion, so it won't run out anymore. For a basic buffer, again, it's a weak base and the salt of a weak base. Well, we'll choose ammonia, but let me make it a bit more clear. Let's say it's ammonium hydroxide. That's just ammonia in water. That actually makes it easier. So this weak base, it dissociates to form ammonium ion and the hydroxide ion. Again, it's weak, so it's only a partial dissociation. If I add acid, well, once again, it forms water, and that water just goes. The equilibrium shifts to the products, replaces that OH minus. Hey, I can add more acid. Forms water, disappears, and we can keep doing that all day. This will take acid and neutralize that acid. The pH won't change. If I add base, well, we've got a problem. I can't really go back towards the reactants because I'm going to run out of ammonium ions very quickly. I've hardly got any. Oh, it's equilibrium, that won't happen. Yes, it does happen in reality. You can't have the reaction move back to the reactants that much. There's not much ammonium. So add more ammonium ions. Where am I going to find those? Well, throw in ammonium chloride. That's 100% soluble. It 100% dissociates, and I'm going to have loads of ammonium. So now when I add OH minus, I can go back in that equilibrium.